This is the brief on optimization using Kuhn-Tucker conditions. So what we're looking at here is a really powerful method for finding the best possible outcome for a goal, even when you're dealing with a bunch of non-negotiable rules or constraints. Okay, first, to tackle this tricky non-linear problem, we use what are called the Kuhn-Tucker conditions, or KKT for short. We kick things off by setting up a Lagrangian function. And really, all that does is combine our main objective with all those constraints we can't break, using special variables called Lagrange multipliers. These are the key, because they tell us if a rule is actually active or not. Second, the heart of the method is just systematically testing the possibilities. You see, we have to look at 4 different cases, depending on whether those multipliers are 0 or non-zero. And it turns out, we got to eliminate the first 2 cases almost immediately. The answers they gave us just flat out broke our constraints, so they were a no-go. Finally, the real solution popped up in case 3. This is the one that satisfied all the rules and gave us our optimal values. And case 4 was also a bust, but this time it was because one of the Lagrange multipliers came out negative, and that's a strict violation of the KKT conditions. They have to be non-negative. So the KKT framework essentially funnels all these complex constraints and variables down to a single optimal solution. Here is a really specific nonlinear optimization challenge. How do you find the absolute minimum value for a function when you're also juggling a couple of strict inequality constraints? It's all about finding that one perfect sweet spot. Okay, so first up, the whole method really centers on establishing these 4 Kuhn-Tucker conditions. To do that, you've got to set up what's called the Lagrangian function. Just think of it as your master equation. It pulls together your main objective and all your constraints using these things called Lagrange multipliers. These conditions then become your essential checklist for any valid solution. Second, once you have that checklist, the real work begins, a systematic case analysis. And the engine driving this is something called complementary slackness. It's a pretty neat rule. It basically says either a constraint is pushed right to its limit or its corresponding multiplier has to be 0. So you go through these different scenarios, and what's interesting here is that a bunch of the initial attempts, they just didn't work. They led to contradictions, so they got tossed out. And that brings us to our final point. The actual optimum was found in the one case where both of those Lagrange multipliers were non-zero. And what does that tell us? It means both constraints were active. They were both binding at the same time. The resulting solution passed every single test on that Kuhn-Tucker checklist, which is how you know for sure that it's the constrained minimum. This whole method of defining conditions and then systematically testing every possibility, well, that's exactly how you pinpoint the perfect solution for these really complex, constrained problems.